Since I'm my own host, I will not introduce myself, besides saying that, as you can tell from the subject, I'm interested in mathematics. Now, this loaded word, theoretical, I put here on purpose to make clear that this is interesting theory for reasons that I'm going to explain. I don't believe this particular thing has immediate glaring applications. It's more of nice to know. Now, it is related to very practical things. I did write quite a successful program to find the nearest neighbors. However, the practical aspects are different. The reason why I chose to talk about this is because of the mathematical interest. It's, in my opinion, a very beautiful theory. So let's go. First, introducing the problem. And I introduce it by an example. Suppose that we are given a set of bit sequences. And most of them are pretty random. But there are few, say there is a pair. I put in them here, one next to the other, so that the comparison is easy, that are more likely to be the same than the rest. So the way to find it is that if we go through all the pairs and compare between each pair, compute the Hamming distance, we'll find that this pair is exceptionally close. Now, when you are talking about small numbers, of course, going through all the pairs is very easy. But when you have tens of millions, and if we'll be able to, maybe even billions of things, then you need to do something better than looking at all pairs, because there are just too many pairs. So this is the general problem. Now, here I can define a very particular model problem by saying that, all right, I have n sequences of bits. The bits are random with probability half 0, half 1. And there is one special pair such that the probability that bits are similar is not a half, but p, where p is greater than half. So the way to present is this: there is a probability matrix of showing in that special pair if you have the probability of having 0 both here and there is p over 2, 1 the same, while having 0 in one and 0 in one sequence and 1 in the other sequence is 1 minus p over 2. Now, this matrix tells the probability of the special pair, but if you are computing the marginal probabilities, meaning summing this and this, we have half, summing this and this, we have half. So that pertains to all those sequences that have probability half-half. So this one matrix encodes how such a thing is generated. All right. Now, this is an example problem completely defined. Now, what do we know about it? First thing is that we need enough data in order to be able to pinpoint the correct pair, even if nobody limits our computation. Because it could be that we just can't tell it. If p is close to a half, for instance, it will be. So when can we do it? So we have information theory. The amount of information in the pair is about 2 log n, or log of n square, or half n square. Now, the amount of information that I have in each single bit is the information function of p. Well-known function. So it is 0 when p is a half, no information, up to log 2 when p is 1, which is the perfect thing. Now we have d bits, so the total information is d. times I of p. So I take the difference. Now, what does this number mean? If this is negative, it means that, yes, I have enough information to pinpoint the pair. If it's positive, it means, no, I can't pinpoint it, but maybe I can restrict it. I can restrict it to a size of n possibilities. This is standard information theory. Of course, the question is computational. How much effort do I need to do? So this is, again, standard. So what we do is that we randomly select a subset of the coordinates, subset of k coordinates, where k is about log base 2 of n. Why that? Because we are going to look at the values in these coordinates. The number of values possible is 2 to the k, which would be approximately n. So it means that each of the sequences will get sort of a place of its own. So we have buckets. The buckets, we throw in a sequence to the bucket according to the value of its coordinates. So let me go back. So if I take the bucket to be the first 3 coordinates, you see that this one and this one would fall to the same bucket. And together with this is a bucket of size at least 3. Here I have another bucket of size 1, and here I have another bucket of size 1.
While you're on that slide, can we review your terminology there? What's the big N and the little n referring to again?
Okay. The little n is the thing that we are going to see a lot. This is the number of objects between which we are trying to find the pairs. The big N is sort of a fleeting acquaintance. It is when I'm looking at the information theory, how many possibilities for a pairing I have left once I fully analyze the data. So it's the difference between the necessary amount of information that I want in order to determine a pair and the amount of information that I have. In most cases, this difference is negative. So though it's written as a big N, it's actually a very small number.
Another question. So in the probability matrix, the probabilities should sum to 1, right?
Yes.
But you have it divided by 2.
Because here, p plus 1 minus p is 1 divided by 2. So this sum is a half. This sum is a half. And together, the sum is 1. Now, this is not a transition matrix. It's a probability matrix. All right. So we saw that we are choosing random k coordinates. And there, what are the chances that the 2 members of the pair will indeed fall into the same basket? It's p to the k, because the chance that they agree on a single coordinate is p, which is about n to the log base 2 of p. So this is a probability. It could be quite small. And this is the chance that one try that we made. We chose those coordinates. We threw into baskets. What are the chances that we found something? The chances are something. So in order to be able to find the correct pair, we have to make several tries. In each try, we randomly pick some subsets of coordinates and throw into baskets. How many tries do we need to do? Exactly the inverse of this number. So that's the number of tries. Now, in each try, on the average, we have to make n comparisons. Because in each basket, we expect very few elements, 1, 2, no more. So number of comparison would be of order of n. So altogether, the number of comparisons that we need is n times this, which is together n to the log base 2 of 2 over p. So we can check now that if P is 1, that everything is perfect, then this is the work is of order n, which means we just have to go and read the data. This is the best case. The worst case, when P is a half, then this is n squared, meaning we have to go and compare everything. We can't do anything. So these are the extremes, and the probability goes between them. Now, I highlighted here two things that I want to stress. One, why do I talk about comparisons? I mean, you would say that the natural unit would be just, say, bit operations. The reason why I talk about comparisons is because, for instance, if d, the length of the sequences, is very, very long, and we would say that then when we go and compare one to another, it's work d, then you would say that the work goes to infinity with d. But actually, we need to take only few of them till that we are certain. So usually we just need to take a logarithmic number. Also, it could be that the data is sparse, so that we have an efficient representation. So I don't. So this is the reason why I don't want to go and count how actually I'm making the comparisons. I'm just counting the comparisons. This is one thing. The other is that I'm claiming that this analysis is valid only when the amount of data that I have, the length of the sequences, is large. Why is that? I mean, apparently what I did before is relevant no matter what this is. The reason why this is necessary is that the analysis that we did is correct once we make our first try. But when we make our second try, we might pick on the same coordinate, so that our tries are not independent. So when D is large, they are independent, and then when it's valid. When D is small, they are dependent, and the actual expression is more complicated. All right, so this is the basic model problem, and it's a standard simple solution. And this is the foundation for everything else. So if there is question about this, better ask it now.
So this is more or less what's called a locality-sensitive patch.
Oh, yeah, of course. I mean,
okay.
when I'm saying standard, meaning there is nothing that I've contributed here in any way. I'm just presenting the basics. It's well known for a long time, definitely. Yes?
So how would each term change when you have not bits, but
all right, so you can see that you can do the same thing if we had, instead of bits, 3 possibilities, so on, it wouldn't matter. Now, what would matter, of course, if you are getting to a more complicated matrix. And then, when the matrix is small enough, you can say that things work sort of the same principle, but they're just more complicated. But you can go to extreme cases and have continuous distributions, etc. And then, though some of the principles remain, it might be quite hard to work the analysis in practice. This, like many other things, this is an analogy to what you have in information theory. Information theory, they start presenting you those nice bit examples, but then somewhere further away, you have electrical engineers working with all those continuous signals. So in principle, you could have this here too. All right, we started with one example. Now, I want to present another example. This is a very important example, and this you wouldn't find so prominent in the literature. And so this is sparse data. Now, the kind of problem that I worked with is a sparse data problem, and I believe that this sort of problem is very, very common. So the matrix there is something of this nature. What does it mean? It means that most times we have zeros. Zeros everywhere with a very large probability. And the probability, so that if you look at the marginal probability, 1 minus 2 epsilon 0, and just 2 epsilons once. All right, now, what's your impression? Suppose that you are given a large amount of data, D as large as you wish. Is this problem easier or harder than the previous problem with a reasonable p, say p 3/4? What's your intuition?
You want us to say it's harder, don't you?
Of course. Well, the surprising thing, or not so surprising, if you think about it, it's actually easier. There is power in sparsity. And I want to show you why. So again, the method that I'm presenting is a standard method that's done long before me. It's usually attributed to Broder, though actually there is an earlier a publication of Udi Manber that somehow he didn't get his name attached to it. But he says that he went to search, and on the whole, he's not sorry that he went to search. But this should be attributed to him too. And again, the approach is bucketing. But here, you have to be a bit more careful, because if you just take a random subset of coordinates, it might well be that they are all 0, because there are so many zeros. So you want to have sort of a certain number of ones. Now, a good practical way to arrange it is the following. You rearrange the coordinates in some random way, and then for each of the sequences you look, where are the ones, starting in that order. So the first one is here, the second one is there, the third one is there, and you're looking at the k of them. And the locations of these k's, this is what determines the bucket. It's a very reasonable system. Now, let's see how it performs. This is actually an upper bound. I'm not trying to compute exactly how it performs, but showing that it does at least this well. So the number of coordinates that we take is log n divided by log 2 epsilon. Why is that? Because what's the probability that 2 unrelated points fall into the same bucket? It could depend on a large number of coordinates, but we know that at least k of them, so look at the first, at least k of these are ones. Now these ones, they must be ones also in the other. So the probability is at most 2 epsilon to the k. Now this choice of k is so that this is order of 1 over n. So that again, we expect the buckets to be of a small size. Now, when we do this, now what's the probability that 2 related sequences fall into the same bucket? Well, let's look at the first m coordinates. M is arbitrary. I can choose it whatever I want. Now, if I know that those two agree on those m values and that k of them are ones, then it's fine. So we have at least a probability of choosing those k ones out of m. This is the probability of having those two values ones. The probability of having those two epsilon. Well, not the most pleasant expression in the world, though we'll see much worse. And we can rewrite it like this, which looks even worse. But the point here is that a choice of m, a reasonable choice, this is so that the expected number will be k, gives this binomial expression that is a sort of order unity, or 1 over m. So you do the computation gives that the amount of work is like this. You have n to the 1 plus something which is small. Now, this is what I want to stress. The larger epsilon is, the smaller this addition, and the better we are. Now, even though, notice that each one, the probability is suppose that I know that there is one here. The probability that it's preserved in the other sequence is just a half. Nevertheless, because those things are so rare, I can make a very good determination. They are very powerful indicators. Now, also a thing to notice that, again, you can think of the distances here as Hamming distances, but if you look at the probabilities, really quite funny things happen. So, for instance, the sequence that with no ones whatsoever is as close in probability to something as itself. Because you see that here, this epsilon are the same. And we could, of course, take an example of making this, say, 2 epsilon, and then it would be even worse. So the metric considerations become a bit tricky. It's not really right to look at it as a metric space at all. All right, so this is the sparse example. Any questions about it? All right. Now, since I put that word theory in, there is no way for me to avoid mentioning the leading theory attached to the subject. Most papers take this approach. And if I don't mention it, I would be asked, well, how do you compare with this? Now, the approach that I take is a probabilistic, while this approach is worst case. So it's apples and oranges in one sense. Nevertheless, there are some comparisons to be made. So what this theory says, actually, the algorithm that it's based, it's even a simpler version of the bucketing algorithm that we saw at first, except that coordinates are chosen with replacement. So you can have the same coordinate chosen few times, which seems a bad idea. But it makes the analysis easier because then you have independent choice. And what turns out is the following. Suppose that you have a problem of trying to find the nearest neighbors, and there is a ratio C between the random distance between just 2 points anywhere, and the distance of the right pair. Now, if you have this ratio C, then you can do it work n to the 1 plus 1 over C. So the larger C is, the larger the ratio between the random distance and a pair distance, the better you can do. Now, this is sort of a quote. I mean, I'm not showing why it is, though it's quite simple. Now, also, there is a lower bound, quite an interesting paper. And this lower bound is actually valid not only from this point of view, but also from the random point of view. And it shows that in some sense, under some assumptions, you cannot do better than a power which also goes near 1 when C gets large. Now, let's see how it does in the particular examples that we saw so far. So in the first example, the ratio, it's very easy to compute because the random distance is half D. 2 random points will agree in half and will be different in half, while the pair distance is 1 minus P times D. So the work that we get is like this. This is worse than what we had before, but you can say, OK, this is sort of a general worst case thing. So, well, we might have something worse. Now, let's take the sparse problem. So here, we have those metrics. So two random ones each one of them will have 2 epsilon 1s, and there will be little intersection because epsilon is small. So the distance would be about 4 epsilon d. While 2 correct ones, each will have 2 epsilon 2, but epsilon of them would be the same. So the distance would be about 2 epsilon d. So the ratio C is 2, which brings a work like this. And notice that there is no factor that drives this to 1 when epsilon goes to 0. So I'd say that this is quite unacceptable. Now, of course, one can say that, all right, this is because this is and it is a very general bound under worst conditions. But maybe when we look at the actual method, things work better. Now, you can tell me if I'm wrong, but I really did my best to look and see which methods they recommend. So I went and Googled locality-sensitive hashing, and there they point a paper, locality-sensitive hashing scheme based on p-stable distributions. I look in there, and there is a particular method they recommend exactly for sparse data. So I believe I did my best to see the recommended thing, and it is quite a clever scheme. What it does, instead of looking at coordinates, it does random projection. The idea goes to the Johnson-Lindenstrauss theorem, but here, instead of using normal or discrete variables, they are using Cauchy variables, C, which have a distribution without variance. And the reason why they're using them is because they go well with the L1 matrix. And so what they do is that for each sequence, they're taking and computing a sort of a signature, which is 1 bit that is computed out of the whole sequence by taking combination of values and looking at the sign of the thing. And you need to take, again, k of these random signatures with different values, project into the buckets, and see what happens. Now, the idea of random projection seems very compelling. You start with a problem in 20,000 dimensions. You do a random projection. You have now a problem in 20 dimensions with the distance structure about the same. This is what the theory guarantees, and this is what is actually delivered. Could anything be wrong with that? Well, if what we were to do is to go choose pairs of points and compute distances, then there is nothing wrong with that. The distance that we would get in the 20,000 dimensions is about the same as the distance that we will get in the 20 dimensions, and everything is fine. However, notice that the methods that we did before, did we go just to pick pairs of points and compute their distances? No. We looked at particular coordinates. Now, once you go and do a random projection, those coordinates are lost forever. Now, the effect that it has is quite dramatic. So I think that I wouldn't go now through the details. They are written and they are not very complicated. But it turns out that this particular method on this example has performance. Not only that this doesn't tend to 1, it's even worse than what we had before. Now, I actually heard from 3 different people, independent, who tried the random projection approach, not necessarily using Cauchy variables, but this thing doesn't depend on the Cauchy. And each one of them found that it didn't work. This is why. Any questions about that?
magnitude, if you project to a large number, you have a problem that resembles the original problem, would have the same bounds?
No, it doesn't matter much. What matters is how you do the projection. If by doing it you go and you scramble your bits, then things are bad. Of course, if you compute one projection to a large number of bits and do it in a non-scrambling way, then this is fine. But this is again the approach that we started off. The idea of going and combining all sorts of coordinates together by summing them up is the destructive thing. And if you think of it, it's quite obvious, actually. How could they think otherwise? All right. So this was a sort of negative part, and believe me, this is the sort of thing that I can't avoid because it is the reigning theory. Now, the way I prefer things is taking the probabilistic model of having a matrix. Now it's not necessarily 2 by 2. And I have a data that is randomly generated by it, and I have a certain pair, or could be many pairs, it doesn't matter, that are related, the others are not related, and it's a question of what we can do under the circumstances. Now, the general question of what we can do is just too difficult. I mean, if I were able to prove that any algorithm here couldn't do better than something non-trivial, then for me to prove that P is different than NP would be quite simple. Since it isn't, no, I will not do this. So I must restrict my class of algorithms. I can't allow just everything. The class of algorithms that I consider are, well, the sort of the things that we saw before, bucketing algorithms. Meaning I have buckets, I throw things into buckets. Now, all the algorithms that are actually practiced are bucketing algorithms. However, I insist not just that I have bucketing algorithms, but that I have the buckets fixed in advance, independent of the data. Now, many algorithms actually construct the buckets using the data. Now, I cannot prove things about this situation because you could do a very complicated construction, and then, who knows, by miracle, things work. I certainly couldn't prove that they wouldn't. However, when you have random data, I'd say that using the data in order to generate the buckets doesn't seem to give much value, because think as long as we are not using our special pair and you are using everything else, then everything else is just random. You might as well have a fixed buckets. So the only game that we have is by how this special pair affects the buckets. The intuition is that it doesn't help much, but of course I can't prove such a thing. All right, so what does the bucketing algorithm mean? I have a list of buckets. Now here, the buckets are actually pairs, because this is another generalization. Instead of having just a single set of sequences, I have, say, 2 sets, and I want to compute pairs between one and the other. Now, this allows also to consider a non-symmetric problem when we have a large set and a small set. So when I'm taking buckets, I'm allowing buckets in one sequence and buckets in another sequence. Now, an example of why this sort of thing would be necessary is that if you have a really general problem, you could have that a special pair are anti-correlated, where one of them is 1, the other one tends to be 0. in order to design buckets there, of course, the buckets for the one and the buckets for the other must be different. Otherwise, there is no way. So in general, I'm really forced to do this. Now, so I have a list of buckets. And also, before I describe the bucketing procedure as composed of tries. I do first try, throw into buckets, do the second try, etc. Here, the description is that I put all the tries together. Here is the whole list of buckets. I go and try on them. All right. Now, what are the properties of such a thing? First of all, there is some success probability. And that's just that if I'm looking on those sets, the probability that my pair would fall into them, this is a success probability. I have probability that both of them fall into this bucket, or into this bucket, or into that bucket. This union is the set that I succeed, and its probability, this is a success probability. This is obvious. Now, the work probability is a bit less obvious. I have here this expression. What does it mean? Now, this, I have n0 is the number in one set, n1 the number in the other set. You can just think of them both as equal to n, if you don't want to think of different sets. So n0, the probability of bucket 0, how many elements of the set 1 I expect to fall into this bucket. This, the number that I expect to its companion. So the multiplication is the number of comparisons. Adding all these things is the total number of comparisons. So this is certainly an element of the work necessary. However, this is not the only thing. If we allowed only this, we could make very, very, very small buckets and do, it seems, a little work. There is another work of just throwing things into buckets. So this is how many elements are thrown into the first bucket. And we have to sum. Because even if we do things and we don't succeed in order to match pairs, we still have to throw them in. So all this expression is certainly a lower bound. Now, can such a thing be realized? Now, this thing is real. This is just a number of comparisons. But throwing things into buckets, it might be necessary to do more work. You can think of an algorithm that you have a prepared list for each element to which bucket it belongs. You see an element, you make a lookup, and that's it. Then this is really the amount of work necessary. But this is a bit cheating because the list, their size is exponential in n. So in order to realize such a thing, we actually need to do a sort of a tensor product. Make a projection depending not on all the coordinates, but on some of them. Make a projection on the others, etc. And combine them in a tensor product. And then such a thing can be approximated. At least I hope that the idea that such a thing is an absolute lower bound should be clear, hopefully. All right, and now the result. And this is something that I find quite surprising. Now, I wrote the information theory bound at the thing that we had before so that we can compare. So now I remember that before we had d times the information. Now I allow that to have different matrices in each place. Sort of generalization. Then the information bound this, the log of the number of possible pairs minus the available information. When this is negative, we have enough information in order to determine which is the correct pair. Now, this is my result. It says that the amount of work is supremum over something that depends on the size of the sets, the success probability, and I have to subtract information functions. Now, this information function depends on the matrix, but it has 3 parameters. And with particular values of these parameters, it is the same as the original information function. This expression certainly takes some time to get used to. First of all, notice that though it's quite complicated, it's neat in the sense there are no funny constants. There is no big O, little o, c, not even 2.3. Everything is just right. Now, yes?
U is infinity.
Mm-hmm. Well, you can say that U is infinity when S is 1. Probability of success is 1. Now, in actuality, in order to ensure probability of success 1, it's necessary to do a large amount of work, say n squared. So the realistic thing is to put S not 1, but say 1 minus 1 over n or something. And then mu wouldn't be infinity. It would be just something large. Now, what's the meaning of this sort of statement? Now, we have lots of pieces of information coming from the different coordinates. So now think that we have this bunch of bits, and think of it as sort of given, fixed thing. For this fixed thing, we have those fixed parameters. And now just look at how making a small change in here changes the behavior of the expression. So for instance, if we increase the size of the set from n0 to 2n0, what happens to the work? It increases by a factor of 2 to the lambda 0. So this lambda 0 is actually the exponent of showing how the work increases with the size of the first set. Now, how it increases with the second set, mu, how it behaves when we are changing the requirements for success. And this is how much we gain from each piece of information. Now, the how much we gain is a bit tricky, because think of the situation that we have lots of data when this sort of goes to infinity. Then each particular piece of data has very, very little value. Not only that each one of them goes to 0, the sum altogether would go to 0 too, because the information that you have in each one coordinate is almost contained in the others. So in that situation, when d is large, the meaning of all this expression is really the question of for which values of lambda this information goes to 0, this information function. Of course, you could have data of different quality. So you could have some pieces of data. For them, the information has a large value, and they reduce the amount of work considerably. Now, it's not necessary to work with all those parameters. You could take the n0 equal n1, lambda 0 equal 1, lambda 1, and they take the mu large towards infinity, and you are left with sort of one parameter. But one parameter is necessary. It cannot go and be just like that. Now, this is a lower bound. And there is also a statement that this is asymptotically correct in some sense. So the way it's proven is also a bit reminiscent of information theory, that the lower bound is proven by sort of information-like inequality. And the upper bound, the claim that we can achieve such a thing, is by constructing a random bucketing code. So I will show in a very cursory way the idea behind the construction and the proof, and then I'll try to answer questions. It's not a simple thing, so it certainly takes time to get used to. Now, this information function is not a simple thing, not a surprise by now, though the expression does have a sort of beauty of its own. The Kullback-Leibler divergence, or you can just say the entropy distance, plays here a very large role. This is a sort of very information theoretic expression, and it goes here to a large extent. Now, how such a thing is proven? So in order to get the idea, just let us take the case when we have lots of data. And then the inequality, this is also a quite interesting inequality, that the work is less than or equal success probability times powers of the size of sets. So when we take this example and we ask, plugging those things, how well we can do, turns out that instead of what we had, n to the log base 2 of 2 over p, we can approach n to the power of 1 over p. And that's the optimal power. Another thing is that if we have an unbalanced set, one size n1, the other of a smaller size, n1 to a smaller power, and when this power is small enough, we can do with a linear amount of work. Also quite a surprise. How are these things done? So the construction, so for instance, in this case, as I said, it's just done by random buckets. We are choosing random points, drawing a humming ball around them that contains about 1/n of the data. So this is the basic thing, and we have to do tensor products of these. And it works. So the same approach of building random codes in information theory works in here too. In the more general matrix, the construction is more elaborate, but again, it's a random construction. As for the inequality, how such an inequality is proven, so the crucial step is showing that if the information function is 0 for 2 matrices, then it's equivalent for it being 0 on their tensor product. This is working some inequalities. None of them is complicated, but there are some of them. So this is not a thing to present here. And then, in order to prove the sort of this, by the way, is a thing of interest by itself. Look at this inequality. What it says is that the probability of having a rectangle is less than or equal products of of its marginal probabilities to some parameters that have a relation between them. if you know of the Talleyrand inequalities or other probability inequalities, you will find this sort of thing interesting. And this is proven now very simply, and that's the idea that we had before, that we show that from the information of a single matrix, I get information of the tensor product. Then I can just look at the tensor product and reduce to dimension 1, insert into the definition, and I get the inequality immediately. And then there is another, I won't go through this, but this is all what's left. Very, very simple and neat inequality. So this is essentially it. As you get there, there are certainly non-trivial details. The information function is not simple to compute. It's not like what we had, the information that there is just a formula involving logarithms. Here it's a thing that you really need to run a small computer program to compute. But it is computable, and it gives bounds as to what you can achieve with using buckets, no matter what you do. So all this thing is a sort of a parallel information theory, more complicated than the standard information theory, valid for this particular case. So I got, at the end, I have a list of bibliography if people are interested in the theory of these things. But first, questions. Well, I don't interpret this as that I made everything clear. Well.
Typical nearest neighbor problem would be, say, finding duplicate videos. You got a big database that we compute locality-sensitive hashes on as we get them, and then when we get a new video, we compute the buckets for that one, and then we'll try to figure out if there's one in there that it's close to. So that's like your unbalanced set problem where you've got a set of size 1 and a set of size n0. Try to find if there's one match to that one view.
Yes, but in this situation, the large set is being pre-processed.
You're right, it's been pre-processed. So now the question is, if you have such a scheme where you, and it seems to me like that's one of the big advantages of the whole LSH thing, is that you can pre-process so that the queries become fast. Is that the right interpretation? And how much work is there if the buckets have all been pre-computed? How much work is it to compare that one new thing to that large set? Is it it's still fine. The bounds that you have, if you divide by n, it would still be the work of finding one using the pre-computation. However, the way it's presented here, the amount of data that you have to keep is very large. So usually when you have the situation that you pre-compute things, it's important for you that the pre-computation will result in a compact data, not much larger than the original, while this can violate it. This is certainly a drawback of this general approach. Okay, so thanks for coming to hear me.